The towering antenna, like a silent sentinel, offers to the passerby little evidence of the vital role it plays in the drama of radio communication. The antenna takes many forms. These vary from a simple vertical conductor directed in space to the highly complicated installations used in radio transmission. Could we see electrical impulses and radio waves, we would see moving over the feed line from the transmitter to the antenna, traveling waves carrying the energy which the antenna radiates. At the antenna, we would see electromagnetic waves being generated and speeding up in all directions. These waves move through space at the speed of light. The frequency of the traveling waves on the transmission line and the radiated waves sent out into space is the same. In diagram and in slow motion, we may picture a high-frequency impulse moving over a wire as a traveling wave. A traveling wave on a conductor keeps its speed and form until obstructed in some way. If such a wave comes to an abrupt end of its conductor, that is, to a position of infinite impedance, it is reflected and turns back in the opposite direction. If, however, another wave following the first one meets the reflected wave, the two unite and the standing wave results. A standing wave does not move along its conductor, but continues to oscillate in one position. If energy is supplied at the periodic frequency of the standing wave, it will oscillate indefinitely. A complete standing wave consists of two opposing peaks of electric energy. A half-wave antenna resonates at the frequency and wavelength of half of a standing wave. This animation represents the distribution and changes in current on the antenna. The half-wave antenna is often referred to as the Hertz antenna. The full-wave antenna resonates with two alternating peaks of current, functioning as a complete standing wave. On the half-wave antenna, current is at its maximum at the center, while it is minimum at the end. Voltage is high at the ends and approaches zero at the center. We may picture the complete half-wave with both current and voltage components resonating on the half-wave antenna. When the voltage difference between the two ends is greatest, the current flow in the antenna is least. As voltage increases, current decreases, reaching minimum current at the time of maximum voltage. Each period of high voltage and low current is followed by a period of low voltage and high current. This, in turn, is followed by another period of high voltage and low current, with the polarity of the antenna reversed. The rate at which the conditions of voltage difference and current movements change constitutes the frequency at which the antenna is resonating. The Hertz antenna may be resonated not only by the half-wave, but also by any harmonic of the fundamental. That is, a full wave, 1½ waves, 2 waves, etc. Any multiple of the half wave. In practice, however, the antenna is usually designed to resonate to the half or the full wave only. We may picture a half wave resonating on an antenna. Now, if it were possible to drive it halfway into the earth, it would continue to function as if the earth were half of the antenna. Such an antenna is an electrical unit with the earth, no insulation of any sort being used. An antenna of which the earth makes up the lower half is known as a grounded or Marconi antenna. It has zero current at the open end and maximum current at the grounded end. The open end is a point of high voltage, while the grounded end shows zero voltage. A grounded or Marconi antenna is the fundamental quarter wave antenna. It will resonate at any odd harmonic of the fundamental, at the third harmonic, for example. At another time, it may be made to resonate at the fifth harmonic, the seventh harmonic, or any other odd harmonic of the fundamental quarter wave. But an antenna will not function alone. It is always part of a receiving or transmitting unit. Where the transmitter is at a distance from the antenna, a transmission line is necessary. The transmission line should carry only traveling waves. If any part of the energy is reflected back on the transmission line, standing waves result, and radiation falls off. Here we see both traveling waves and standing waves on the same transmission line. Every effort is made in the designing of an antenna and transmission system to prevent the development of standing waves. We may attach a single wire to an antenna as a transmission line from the transmitter. We attach this at a point about 1/7 of the antenna's length from its center. Since the impedance range of the half-wave antenna is from about 3,000 ohms to about 72 ohms, the impedance of the transmission line and of the antenna at that point will match. Meeting no impedance change, waves are not reflected back over the transmission line. In a two-wire transmission line, the closer the spacing, the lower the impedance. So it is possible to use a twisted pair of insulated wires, the impedance of which will equal approximately 73 ohms at the center of such an antenna. Energy may be fed directly to a half-wave antenna by coupling the transmitter output inductively to the center. Center feeding of a half-wave antenna is current feeding, since power is introduced at the point of high current. Voltage feeding inserts power at a point of high voltage. This is accomplished either by direct coupling to the tank circuit of the transmitter or by an inductive coupling to the tank circuit. The antenna should be of such length as to approximately equal the wavelength to be radiated. If the actual length of an antenna is shorter than the desired length, it may be made to function as if it were longer. To obtain this desired effective length, a loading coil is placed in the antenna. This coil, by adding inductance, increases the antenna's effective length. The antenna resonates at a lower frequency. If an antenna is too long, a condenser may be placed in it, decreasing its effective length. Thus, a long antenna resonates at a higher frequency than it otherwise would. With the introduction of a tap coil and a variable condenser into an antenna system, the effective range of wavelengths is increased. This allows for accurate tuning over a wide band of frequency. In a receiving antenna, the length of wire is not so vital as in a transmitting antenna. Receiving antennas are seldom under 20 feet or more than 200 feet in length. Under a certain circumstance, a very short antenna is required. We can obtain the same effect of length through a loading coil, decreasing its lateral length the same as in the transmission antenna. Basically, all of these different types of antennas act as conductors of electric communication, but each antenna has its own different function with specific requirements. For instance, this is a high-frequency antenna. Simply, it is to radiate the available HF energy in the required direction. HF is still used extensively. For air-ground communication, the HF antenna is gradually being replaced by these very high-frequency antennas. Perhaps the greatest advantages of VHF are freedom from static and smaller antennas. These ultra-high frequency antennas have the same general advantages as VHF. UHF is used primarily for military aviation, which has been allocated a special portion of the radio spectrum. And this diamond-shaped rhombic antenna, which can be easily constructed, offers the advantages of good directivity, gain, and fairly uniform impedance characteristics over a fairly wide frequency band. Usually, the conductors are constructed of twin or triple wire, connected in parallel, which improves the efficiency. This antenna is adapted mainly for long-distance shortwave communications. Here we see some different types of ground radar antennas, which are adapted to many specialized uses. This is a secondary radar antenna aligned with the primary radar antenna. In addition to extending and reinforcing the primary radar, the secondary radar can be made to receive and furnish identification and altitude information through the transmission of coded signals from aircraft in flight. This transponder antenna, located on the underside of the aircraft, sends out a return signal automatically when the beam from the primary radar antenna is being received. In early days, the slow-speed aircraft were equipped with exterior antennas, such as the trailing antenna. The wire is paid out from a reel inside the fuselage. Usually, this antenna functions at the 3/4 wavelength. And the fixed wire antenna, stretched along the length of the fuselage or on the underside of the aircraft. With the rapid growth of high-speed aircraft, all of the aircraft antennas are also being changed. In modern aircraft, most of the antennas are built into the aircraft frame. For example, this DC-8 aircraft is equipped with more than 20 different types of antennas, but none of them is visible. The arrows here indicate the position of the antennas. On the ground as well as on the aircraft, the antenna site is a very important factor in helping the efficient functioning and clearing of obstructions with the maximum radiation of signal energy. It is vital to have the transmitting and receiving antennas elevated as high as possible above the ground. But it must be remembered that their high elevation increases the hazard to aircraft.